Hello, in today's lecture we will learn how to use machine learning methods to estimate autoregressive with exogenous or ARX models of dynamical systems and time series. We will use Keras, TensorFlow and Python programming language. Here is a brief lecture outline. First, we're going to talk about ARX models. We're going to introduce ARX models and give some brief background information. Then, we're going to talk about problem formulation. After that, we're going to talk how to organize input-output data into the matrices that Keras and TensorFlow can understand. And at the end, we're going to explain the Keras code and we're going to give the simulation results. I have created a post that explains all the codes and the theory that is presented in this lecture. A link to this post can be found in the description below and its address can be found here. So let us start with the problem formulation. This figure over here shows a sketch of an inverted pendulum. So what is an inverted pendulum? An inverted pendulum consists of a cart, and on the top of a cart we have a pendulum. If we apply the force F to the cart, the pendulum will oscillate. One of the basic control engineering problems is to find the force F such that this pendulum is stabilized in its vertical unstable position. The pendulum has 2 degrees of freedom. They are the position x and the oscillation angle phi. Now, this pendulum can be schematically represented in a block diagram form where input is the external force applied to the system and the output can be the position x or the angle of rotation phi or both x and phi. Now, in the control engineering literature, usually inputs are denoted by u and the outputs are denoted by y. And so this is the basic block diagram of the system. The input u and the output y are continuous functions of time. However, we usually with some kind of sensor can observe discrete time samples of the input u and the output y. And from machine learning or system identification perspective, it's more convenient to represent the system in so-called discrete time domain. So let us proceed with the discrete time system description. The basic idea is to divide a time axis into a certain number of equidistant discrete time samples that we denote by k. The distance between k and k plus 1 is equal to the discretization time constant t. The output of the system at discrete time instant kt or y of kt will be defined as y and in a subscript we put k. Similarly, we define discrete time input signals. If we feed the system with a sequence or time series of discrete time input signals, the system will produce another sequence of output signals, of discrete time output signals. We assume that we can observe uk and that we can observe the yk signals. We can relate the system input at the time instant k minus 1 and the system output at the time instant k through the so-called state space model. So this is a system state space model. X of k minus 1 is the system internal state at the time instant k minus 1. We can understand the system state as a system's internal memory. For example, if we know the system input at time instant 0 and the system's initial state or the state at initial time 0, we can just propagate the state equation to obtain x1. Once we have determined the x1, we can compute the system output by just propagating the so-called output equation. So the first equation is the state equation, the second equation is the so-called output equation. Now, the main difficulty with the state space system description is that the initial state, or the state at time instant k, is usually unknown. And this creates some challenges when we try to estimate such a model from the input-output data. Now, as I show in the post, whose link can be found in the description below, we can eliminate the system's state, and by doing so, we arrive at a so-called ARX Systems Description. So what is an ARX Systems Description? This system description is purely input-output system descriptions. This system description tells us that the system output at the time instant k can be represented as a nonlinear function of systems past outputs and past systems inputs. So the system output at the time instant k is a nonlinear function of output at the time instant k minus 1, k minus 2 until k minus p, inputs starting from k minus 1, k minus 2 until k minus p. That is, we go backwards in time. The integer p, the positive integer p, is called the past systems window. Now, w is a nonlinear function for nonlinear systems. If a system is linear, w is a linear function. Usually, we need to add a noise term. This noise term takes into account the measurement noise, and it also can take into account some model uncertainties. Why this model is called an ARX model? Now, if we analyze the name ARX, or AutoRegressive with exogenous input signals, the AR part corresponds to this part over here, to past system outputs. And the exogenous part corresponds to external systems inputs. If we know this nonlinear function, and if we know the past systems outputs and inputs, we are able to predict the system's output at the time instant k. This is shown by the following block diagram. Now, we finally can define our problem. So the problem is to train an artificial neural network to approximate yk, given the input data, the past input data, the past output data, and the past input data. Here is a block diagram. So, if we have the past output data and the past input data, we can feed them to a neural network, and the neural network should be able to predict the output of the system at the time instant k. One of the most important and crucial problems in machine learning and in training of neural networks is how to organize our data. Now, the structure of the ARX model already tells us how the data should be organized. So, we will take all the system inputs and all the system outputs, and we are going to organize them in the so-called data matrices. So, this is the first row vector of the data matrix. It is the first row of the data matrix. It consists of the inputs from time instant 1 until time instant p, from the outputs at the time instant 1 until the output at the time instant p. Now, if we feed this row into a neural network, the neural network should give us as an output the output at the time instant p plus 1. We can do this for the time instant 1, we obtain the first column, for the time instant 2, we obtain the second column, and so on. And this is how our training data should be organized. These are so-called samples, the rows are called samples, and X will be called the input matrix and Y will be called the output matrix. We will generate 3 sets of input and output data. That is, we have to have the training data, we have to have the validation data, and we have to have the test data. More details about this organization will be given in our next slide. Now, we use an example of a mass spring system to demonstrate the numerical effectiveness of machine learning methods. So this is a mass spring system. We have a force F that acts on the mass, and the mass is attached to the wall by using a spring and a damper. So if we displace the mass from its equilibrium point, the mass will start to oscillate, and due to the damping forces, it will settle to its steady state or equilibrium point. Now, what is here an input data? An input data consists of discrete time samples of the force. And what is the output data? In our case, the output data is the displacement d. Now, here you can see a typical system's response to the step input force. So we apply a constant force F and the system will oscillate and it will settle again at another steady state point. So for the known system parameters, that is for the mass, spring constants and the damper constant, and for certain initial conditions and for a given force F, we have simulated the system using the Python programming language, and we have obtained the discrete time samples of the force and the distance d. Now, the goal is to learn the ARX model of the system using the Keras and Python programming languages. In the sequel, we explained the Keras code we used to estimate the ARX model. But before we explain the code, let us just briefly comment on the relationship between the state space models and the ARX models. So if we start from the linear state space model, and by performing basic calculations, we can arrive at the ARX systems description. So here is the ARX systems description. Now, here is the Python code we used. So, first we define the system. So these are our A, B, and C matrices in the state space model, in a linear state space model of the mass spring system. The linear state space model has the standard state space form given by these two equations. So this is the state equation and the output equation is given yk is cxk. Now, we define the system matrices. We define the total number of discrete time samples. We define the sampling discretization time t, and we define the past horizon. In this case, the past horizon is equal to 2. However, in the general case, the past horizon should also be determined from the data, but we're going to talk about that in our future videos. Now, the next step is to write a function that is used to organize the data. So these are our data matrices. So, input sequence parameter and output sequence input parameters, function input parameters, are basically vectors of inputs and outputs. The input is the force, the output is the distance. So this function spits out the data matrix X or the input matrix X having this form and the output matrix, or in this case it's going to be a vector, the output Y. So this is how our training, validation, and test data is organized. Next, we generate the training, validation, and the test data. First, we generate the random input control sequence. So, what is a random input control sequence? At every time sample, we generate a random number from a uniform distribution with the support from 0 to 1. So in our case, the force or the input sequence should look somehow like this. Now, we also need to generate the initial condition for simulating the state space model. So here is the initial condition. Then we generate the output sequence by simulating the state space model. The code for simulating the state space model is given in our previous video and the post, and the link is given in the description below. Once we have the input and output data, we call the function, the previously explained function, we form the training and the input training and the output training matrices. Using the similar procedure, we generate the validation and the test data. It should be noted that the training data is statistically independent from the validation data and statistically independent from the test data, since the input sequences in validation data and in the test data are again randomly generated, as well as initial conditions. Next, we define the architecture of the neural network. In our case, the neural network will have the following form. This will be the input layer and this will be the output layer. The output layer only has a single neuron, since the dimension of the output is equal to 1. And we're going to present to such a neural network every row of the matrix X. And if you remember, the matrix X has the following structure. It starts from Y1 until YP, then it has U1 until UP. And similarly, we define other rows. So this will be an input to the network, and the network should predict YP plus 1. The code lines from 4 until the code line 8 are used to define the network. Here we use linear activation function. We don't use bias. Here we set the input dimension. The input dimension is actually the number of elements in every row of the data matrix X. And here we basically, the code line 8, we compile the network. The network is trained using the code line 9, and we record the history, the training history. The training history will give us the validation loss and the training loss. Also, we provide, during the training, we also provide the validation data so we can compare the model performance on the training and validation data. Once the network has been trained, we want to see how this network performs on a new set of input data. We use the X-test data matrix and feed it into the network to generate the network prediction. The network prediction is actually a vector of predicted output time samples, starting from the time sample p plus 1 and ending at the time sample n. Now, we want to compare this predicted output vector with so-called true output vector that is generated by simulating the original mass spring system using the backward Euler method. The code lines 7 and 10 are used to compute the prediction error. The prediction error is a 2-norm of the difference between the prediction vector and the true vector. Now, code lines 12 until 18 and code lines starting from 25 and ending at 37 are used to plot the true output, the predicted output, and to plot the history, the training and validation history during the training. Figure 1a shows the real output and the predicted output. That is the output predicted by the neural network. We can observe that the prediction and real output lines are practically indistinguishable. That is, the network is able to predict the true system's behavior with a high accuracy. Figure 1b shows the training and validation losses during the network training. We cannot observe overfitting here, and we see a very nice convergence. One of the main reasons why the network is able to predict the system output with a high accuracy is that during the prediction, we always feed the true system output. So we always use this true system past outputs to predict the system output at a future time. Now, this is usually not realistic because the network should work offline. So we should use past predicted values to predict the future output values. These code lines are used to generate predictions on the basis of the past predictors. So if we apply the previously described approach, we obtain the prediction performance given by the figure 2a. We see that the prediction performance is slightly deteriorated. However, the prediction performance is still good. And here we compare the prediction errors at certain time instance between the two approaches. The offline approach is the previously described approach, and the online approach is approach when the true system outputs are used to generate the predictors. This is the end of this lecture. In our future lectures, we are going to discuss how to select the past window P, and we are going to test the presented approach on more realistic examples of physical systems, and we are going to use real experimental data. Thank you very much for your attention.